Hey everyone, today we're going to pull back the digital curtain and take a look at the invisible battle that's happening every single time you send or receive data. It's this constant, hidden fight for clarity, and we're about to meet the heroes and the villains. So let's get right into it.
I mean, we've all been there, right? You're streaming something, you walk into the next room, and boom, the connection just tanks. Well, that super common annoyance is actually a clue to a much, much bigger story about how our information travels and the constant fight it's up against.
Okay, so to really understand this battle, we first have to meet our hero, the signal. You know, in the perfect world, sending data from point A to point B would be totally flawless, right? Instant and perfect. And the signal is the absolute key to making that happen.
So this is the really crucial part. Everything you do online, whether it's sending an email, watching a movie, hopping on a video call, all of it gets converted into a physical signal. This signal is literally the messenger, this little packet of energy that's carrying your information across wires or even just through the air.
Now, this little messenger can travel in two main ways. You've got analog, which is kind of old school, like the smooth, flowing wave of a radio broadcast. But today, our world pretty much runs on digital transmission, these sharp, clean pulses of ones and zeros. It's just way more resistant to errors, which is exactly what you need for reliable computer networks.
But here's the catch. That journey from your device to a server and back again, it's not a smooth ride. Not at all. Our perfect little digital signal is constantly under attack from this whole group of invisible enemies that are just trying to corrupt it.
The official technical term for these enemies is transmission impairments. It's really just a catch-all name for anything and everything that can mess with your data, leading to slow speeds, errors, and yep, those annoying dropped connections.
So let's meet these villains. We're going to put a face to the things that make your internet slow. And we'll start with the one that answers our big Wi-Fi question from the beginning.
First up on our list, we have attenuation. This is the silent strength sapper. It's just like how your voice gets quieter the farther away you are. Well, a data signal loses energy as it travels. This is exactly why your Wi-Fi signal bars drop when you walk away from the router. Attenuation is the culprit.
So what's actually causing this? Well, it's just physics, really. In copper cables, energy gets lost as heat. With wireless signals, that energy is just soaked up by the air, the walls, pretty much everything around you. And of course, the farther a signal has to travel, the weaker it's going to get. Simple as that. Our second villain is noise. Think of this as the party crasher of data transmission. It's any random, unwanted energy that gets mixed in with your clean signal, which makes it way harder for the receiver to figure out what the original message was. It's exactly like trying to have a conversation in a super loud, crowded room.
And noise, well, it comes from everywhere. The simple heat from electronics creates what's called thermal noise. Signals from other cables nearby can actually leak over. That's called crosstalk. And then you have these big, sudden spikes from stuff like a lightning strike, or even just a big machine turning on nearby. That's impulse noise.
And our third major villain is distortion. This one's a little sneakier. It's the shapeshifter. See, a complex signal is actually made of lots of different frequencies, and sometimes they don't all travel at the exact same speed. When that happens, the signal's shape gets all warped, and the digital ones and zeros can start to smear into each other, making them totally unreadable. So, our signal is getting weaker, it's being drowned out by noise, and it's being warped out of shape. It kind of sounds hopeless, right? But network engineers have a whole arsenal of tools and tricks to fight back and make sure our data gets through nice and clean. And this is basically the battle plan. For attenuation, which weakens the signal, we use amplifiers and repeaters to just boost it back to full strength. To fight off all that noise, we use things like shielded cables and really clever error-checking codes. And for distortion, we have devices called equalizers that actually reshape the signal back to how it's supposed to look. And you see this stuff in action all the time. You know that 100-meter limit on a standard Ethernet cable? That's there specifically to prevent too much attenuation. Your Wi-Fi slowing down when someone turns on the microwave? That's noise and interference. And that noticeable delay with satellite internet? Well, that's latency from the incredible distance the signal has to travel. So if we can fight all these impairments, is there any limit to how fast we can send data? Well, the answer is a big yes. And it's not a technological limit. It's a limit that's hard-coded into the laws of physics. Let's talk about the ultimate speed limits of the internet. Okay, first, let's imagine a perfect world for a second. A communication channel with zero noise, absolutely pristine. The Nyquist theorem gives us the formula for the absolute top speed in this ideal fantasy scenario. It's all based on the channel's bandwidth and how many different signal levels we can use. So let's make that real.
Using an example from our source material, if you have a cable with a 5 MHz bandwidth and you're using 16 different signal levels, the theoretical perfect world speed limit, according to Nyquist, is a clean 40 megabits per second.
Okay, 40 megabits sounds great in a perfect lab. But as we just spent all this time learning, the real world is anything but perfect. It's noisy. So how does that change the math?
Well, this is where a giant of information theory, a guy named Claude Shannon, comes into the picture. The Shannon-Hartley theorem. This is the big one. It gives us the true, unbreakable speed limit for any communication channel because it takes our main villain, noise, into account. The most important factor here is a value called the signal-to-noise ratio, or SNR. And it's pretty much what it sounds like. It's a measurement of how much stronger your signal is compared to all the background noise. A high SNR is like having a clear conversation. A low SNR, well, that's our noisy, crowded room again.
So, let's run the numbers again. Using a similar channel, but now with a realistic amount of noise factored in, Shannon's theorem tells us the maximum capacity is actually just under 20 megabits per second. Wow, look at that. The presence of noise cut the theoretical speed in half. That is the real-world price we pay for these impairments.
And this isn't just some abstract theory. This stuff is everything. These two theorems are the fundamental principles that guide the design of our entire digital world. From how we roll out 5G to the fiber optic cables running under the ocean, engineers are in a constant battle to maximize that signal-to-noise ratio, to get us as close as humanly possible to Shannon's limit.
So we know the enemies, we know the weapons we have to fight them, and now we know the ultimate physical speed limit. This leaves us with one last, pretty fascinating question. If we're already pushing up against the laws of physics, what kind of clever engineering tricks will deliver the next great leap in the speed of our connections? Thanks for watching.